Pluto is a far-off and puzzling planet. Pluto is a far-off and puzzling planet, which was once an individual member of our nearby planetary system. However, ongoing declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. They propose that this cold world is on a potential collision course with Neptune. But how could this happen, and what would be the consequences of such a tremendous event? Are we witnessing an imminent disaster, or is there something else to this approaching massive collision? Join us as we explore the potential outcomes of a Pluto-Neptune impact. Pluto, a former planet that was reclassified as a dwarf planet primarily due to its erratic orbit, remains a subject of interest and study in the astronomical community. As shown by recent estimates by leading investigators, Pluto's orbit is dangerously close to Neptune's. Both Neil deGrasse Tyson and Michio Kaku are raising alarms about a potentially dangerous crash between these two planets, which could represent a huge risk to Earth. But how could such an event even be possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. However, the interest doesn't stop there. Pluto's orbit is marked by its unusually elongated shape, veering off significantly from the almost round orbits of the major planets. What makes Pluto's orbit even more bizarre is its inclination, which is shifted by 17 degrees to the ecliptic plane. The way Pluto follows its orbit is much steeper compared to the other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its interaction with Neptune's. For nearly 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, contrary to what we might expect from their positions in the solar system. This leads to the common question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers tried to understand its surprising path. Unlike other planets whose orbits lie fairly close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit amidst these complexities is a testament to the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. In Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all interact in a complex way. The terms Amal libration and degree libration, along with the VZK oscillation, are key components of this enigma. According to astrophysicists, what keeps all planets in their orbits is a type of libration. In the case of Pluto and Neptune, this means that whenever Pluto crosses Neptune's orbit, it is situated roughly 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from intersecting. Degree libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned well above their orbital plane, offering an additional layer of protection from potential collisions. Another key element in this situation is the VZK oscillation, named after three scientists, Bond, Zippel, and F, who studied how objects move in space. It refers to how three space objects, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This gravitational pull influences how they move. For Pluto, the VZK helps us understand why its orbit around the Sun is so distinct. Despite Pluto's orbit seeming chaotic, this oscillation helps keep it moving smoothly for extended periods. These factors help keep Pluto's orbit stable, ensuring it doesn't crash into Neptune or drift off course. This three-body problem helps us understand how these forces change based on how space objects pull on each other. Studying this helps us learn more about Pluto, our solar system, and distant worlds and their stars. Mathematical simulations in the late 1980s revealed that despite these stabilizing properties, Pluto's orbit is, in fact, turbulent, with slight deviations in initial conditions leading to enormous differences over centuries. However, these exceptional properties of Pluto's orbit have been found to maintain stability over extremely long timescales, effectively checking the chaos. Later computer simulations helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, impacted Pluto's path around the Sun. Neptune has a special relationship with Pluto in which, for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This relationship helps keep Pluto's orbit predictable. However, Neptune isn't alone in this. Jupiter's gravity also plays a crucial role in stabilizing Pluto's orbit. In fact, Jupiter's gravity alone is enough to ensure Pluto remains on a steady path for many years, even billions of years. So, it appears that Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely through space without running into trouble. These idiosyncrasies are crucial in the broader context of the universe, maintaining control and consistency in celestial bodies' movements. Without these factors, our nearby planetary system would be a much wilder and more turbulent place. Bodies like Pluto could collide with others or be ejected from their stable orbits, leading to impacts on other celestial bodies. For Pluto, especially with discussions about it potentially colliding with Neptune in the future, understanding its orbit is essential. It gives us a clearer picture of the dynamic nature of the solar system. The case of Pluto shows how even the most seemingly unstable orbits can achieve a state of balance through the complex interplay of gravitational forces and orbital mechanics. It also underscores the importance of constant observation and analysis of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the whimsical nature of celestial bodies, and Pluto's orbit is an ideal representation of this whimsy. The concept of orbital tumult, which refers to the delicate dependence of a celestial body's path on its initial conditions, is strikingly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can dramatically alter its long-term orbit. Using computer simulations has been incredibly helpful for scientists to figure out how Pluto moves in space. These simulations use advanced mathematics to show how Pluto and other space objects, like Neptune, pull on each other. By adjusting small details in the simulations, astronomers can see how even minor changes can make a huge difference in where Pluto ends up. In the late 1980s, these simulations revealed something very interesting about Pluto's orbit. Despite having factors like Amal and degree libration to keep it stable, its path can still be chaotic and eccentric. If you start with just a small difference in where Pluto is or how fast it's moving, over many years its orbit can end up looking very different. However, despite this chaos, Pluto's orbit remains stable for extended periods, like billions of years. This means Pluto's journey around the Sun has some order to it, even though it may seem chaotic at first. Predicting future events, especially when they involve unstable orbits like Pluto's, presents significant challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical simulations provide a solid means to understand and predict the future behavior of celestial bodies, they also highlight the limitations of our forecasting abilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or distortion can lead to vastly different outcomes, making precise predictions a daunting task. Furthermore, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we've made great strides in understanding space, the case of Pluto serves as a reminder of how our knowledge of the universe is still limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the position of each planet can significantly influence the stability and trajectory of other bodies within the system. So why are prominent astrophysicists only now raising concerns about a possible crash between Pluto and Neptune? Despite all these complex forces working to prevent such an event, Neil deGrasse Tyson, a well-known astrophysicist and a key figure in advocating cosmology, offers a unique perspective on the mysteries of our solar system, especially the captivating case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the dark realms of space. Tyson's stance on Pluto's renaming is rooted in our growing knowledge of our solar system. He views the renaming not as a demotion but as an important shift in our understanding of the various bodies orbiting our sun. His approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a sign of how much more there is to discover in space. The interest in these questions, particularly the potential interactions between Pluto and Neptune, highlights the dynamic and often unpredictable nature of our solar system. His work emphasizes that the more we uncover about space, the more questions arise, driving us to explore further and refine our understanding of the universe. Michio Kaku, another eminent physicist and futurist, offers a different yet complementary perspective on the same issue. Kaku's interest lies in understanding how large-scale cosmic events, including potential planetary collisions, might affect the future of our solar system. His research on cosmic phenomena and space exploration, combined with his focus on advanced theories of physics, helps shed light on the larger forces that drive celestial events like those potentially involving Pluto and Neptune. Despite the futuristic speculation surrounding the potential crash, there's a more fundamental question. Is this something we should fear, or is it merely the workings of the universe that we have yet to fully grasp? While the idea of a Pluto-Neptune collision sounds alarming, it's important to understand that our understanding of space and celestial mechanics is constantly evolving. The relationship between Pluto and Neptune has been stable for billions of years, thanks to the delicate balance of gravitational forces at play. Still, there are many unknowns about the long-term behavior of these distant bodies. Researchers continue to refine their models of how planets and dwarf planets interact over time, ensuring that we can better predict and understand future movements within our solar system. One of the key reasons that Pluto and Neptune have not collided, despite their orbits crossing, is the phenomenon of orbital resonance. As mentioned earlier, Pluto and Neptune are in a 2:3 orbital resonance. This means that for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This synchronized dance prevents them from coming close enough to collide. The gravitational interactions between the two bodies are so finely tuned that whenever Pluto approaches Neptune's orbit, Neptune is always positioned far enough away to avoid a direct encounter. However, the possibility of future interactions between Pluto and Neptune should not be entirely dismissed. While current models suggest that their orbits remain stable over time, even the smallest changes in the gravitational influences of other celestial bodies could cause shifts in their paths. For example, if the positions of Jupiter, Saturn, or other giant planets were to change over time, the gravitational influence on Pluto and Neptune could become stronger, possibly leading to more significant orbital perturbations. This is why ongoing monitoring of the orbits of these bodies is essential to understanding how stable they truly are. The idea of a catastrophic event like a collision between Pluto and Neptune also highlights the broader concept of cosmic instability. While our solar system may seem calm and orderly from Earth, it's actually full of dynamic interactions that can lead to unpredictable events over long periods. A collision between 2 planets or a gravitational encounter between other bodies could have far-reaching consequences for the structure of our solar system. For example, a major shift in the orbits of gas giants like Jupiter or Saturn could affect the asteroid belt, redirecting objects toward the inner solar system or even toward Earth. Understanding how such shifts occur is not just about the possibility of a Pluto-Neptune collision, but about the broader dynamics of the solar system. Our planet Earth is part of this delicate balance, and any significant change in the arrangement of celestial bodies could potentially alter the conditions for life here. This is why astronomers continue to study the movement of objects within our solar system, seeking to understand how the gravitational dance between the planets works and how it might evolve in the future. In addition to studying the gravitational forces that influence the orbits of objects like Pluto and Neptune, scientists also look at the long-term stability of the solar system as a whole. The idea that our solar system might eventually experience a significant shift, whether through a planet colliding with another or a planet being ejected from its orbit, is part of the broader field of celestial dynamics. As we continue to observe distant objects with new technologies, like the James Webb Space Telescope, our understanding of these forces deepens, giving us greater insight into the future of our cosmic neighborhood. Another fascinating aspect of Pluto's orbit is its interaction with other Kuiper Belt objects, KBOs. Pluto resides in the Kuiper Belt, a region beyond Neptune that contains a variety of icy bodies and dwarf planets. The study of KBOs not only helps us understand Pluto's behavior, but also reveals more about the formation and evolution of our solar system. By examining how objects within the Kuiper Belt move and interact with each other, scientists can make inferences about the early stages of our solar system's history and the processes that shaped its current configuration. In recent years, the New Horizons mission has provided a wealth of information about Pluto, including high-resolution images and detailed data on its surface composition. These findings are crucial for understanding the nature of Pluto itself, but they also offer valuable insights into the larger dynamics of the solar system. New Horizons has helped to reveal Pluto as a more complex and active world than we previously thought, with evidence of glaciers, mountains, and an atmosphere that experiences seasonal changes. The data from this mission may also shed light on the potential for future interactions between Pluto and Neptune, helping us refine our models of these bodies' movements. Finally, the ongoing debate about Pluto's status, whether it is a planet or a dwarf planet, also serves as a reminder of how our understanding of space is constantly evolving. Just as scientists continue to refine their models of Pluto's orbit and the dynamics between Pluto and Neptune, they also continue to revisit the definitions of what constitutes a planet. The discussion about Pluto's reclassification has prompted a broader reevaluation of what we consider to be a planet, sparking curiosity and debate within the scientific community and beyond. In summary, while the possibility of a Pluto-Neptune collision is unlikely in the near future, the dynamic nature of our solar system means that the situation could change over time. The delicate gravitational interactions between Pluto, Neptune, and other planetary bodies will continue to be a subject of intense study. By monitoring these interactions, scientists can refine their predictions and gain a deeper understanding of the forces that shape our cosmic environment.